Hey guys, it's Mr. Haack. Alright, so this will be our flipped week, and let's go ahead and get started. So our first problem that we want to look at is section 2.6, number 6, which we see right here. And they're saying to determine the points on the interval 0 to 5, so 0 to 5 non-inclusive, at which of the following functions f have discontinuities. So where on x do they have discontinuities? And at each point of discontinuity, state the conditions in the continuity checklist that are violated. So let's go ahead and do that. So the first thing we want to do, let's go ahead and zoom in here. Yes, let's talk about what our continuity checklist is and what each of these definitions from the book are and why they're so important. So those definitions are, first, that you have first of all, something can't be continuous, okay, along an interval and be a function. So there's some random function, unless f of a is defined, or f of a equals some point c. We'll just put that it's defined on the domain, where c is a number on the domain of f. And so at every point f of a along the interval of the function f, at any given point a, in order to be continuous there, it must be first defined there. This is a precondition. Okay? So this does not mean that having this alone is enough to be continuous. For example, if I had this, f of a does equal c, but I'm violating a different principle. Okay, I'm violating the second principle, which is, or the third principle. Okay, we'll skip to the third real quick. So in the example I just gave you down there, this principle is violated. The limit isn't the same as the point that's defined. So I just want to make sure that you don't think that having this is enough. Okay, this is a checklist. You need to have all three, and here's why. And then I'm giving you some ideas of why you can see why this wouldn't be enough on its own. Like, it's often the case that when f of a equals a point that it's not this. It's true that more often than not we get a curve like this, but it's not impossible. So merely having this in a case like this would not be enough. Okay, so now let's take a look at the second checklist item. And I guess here I would put exists or put equals c, so, or L. So where L, let's divide these up, where L is some range value, right, ordinate unique to an x equals value. So if the limit at the point equals something, that's certainly a case that we can have. If we had that, like here's the function I wrote up here. What if we only had the bottom branch of what I drew up here? Right? Then this would be true. So if I only had this part, I could have something like this, so that certainly wouldn't be continuous. So this part down here is saying that what you get this way along the function is the same as that which you get this way along the function. And it's the same as what you get at the x value right here, meaning that it can't help but be the exact same thing, and therefore it is continuous. So let's go ahead and look at what rules it violated, and in this particular case, now that we have our continuity checklist down, and we'll go from there. And also, I'm not sure why the microphone's working in mono, but it's working, And we're also going to break the chapters up into itty bitty bits. And we're starting with 2.6. And we're going to do problems 5, 11, 17, 21, and 28. 2.6 and these problems. Alright, so continuity checklist, take a picture if you need to. You can just do equals L, that's prettier. And then just define what L is. Alright, so let's now take a peek at, like I said, number 5. And I will be pausing at times. Sorry, I had to take you through that journey. And so we can see here that we have some different conditions. So what I'd recommend that you guys do is pause the video and try to see what you think that is, and then I'll come back and kind of, when I resume it, which you obviously won't notice the break, I will have scripted my answer for you and thought of some common things that you guys might do wrong. But this is just a reminder that it is a best practice for you guys to pause the video and try to do this on your own real quick, right here, right now, before I answer the problem. Okay, and hopefully if you took some time like me, you will have noticed that on number 5 here, we're discontinuous at a few different points. And those points of discontinuity are 1, 2, and x equals 3. Now you might be inclined to include x equals 0 and x equals 5, but you can't do that because those aren't even on the domain of the function. And so remember, coming over here to our notes, okay, I'll zoom in a little bit for you guys. We have to remember that this function is only defined on 0 to 5. Okay, so let's go through each type looking at the graph here on the left. So at x equals 1, f of 1 is undefined, so it violates condition 1 right away. It does have a limit defined, the limit, the one-sided limit to 1 from the left and the one-sided limit to 1 from the right do equal the same thing, but it's simply just not defined there, so it can't be continuous, because again, we're talking about leveraging limits to discuss whether functions are continuous or not. Okay, so we're using the language of limits to be a more powerful tool for describing functions. So again, non-inclusive boundaries on 0 and 5 here, and therefore these are not to be evaluated. These are not even part of the domain, so we can't assess continuity there. It's undefined there, but we can't assess continuity because there would need to be points defined to the left of it in order for that to be a question of continuity or not. It can only be considered for continuity up until the point at which it ends, which is before where it's undefined, both here and here. So I know students get confused about that, so we're going to cross that one off the list and continue down our list. Check on the first one. So now let's look at the discontinuity at x equals 2. We have jump discontinuity here, just jumps to this point here, and then it's back down over here. So what rule is violated here? And the rule, yes, the rule that's violated here is condition 3. So condition 3 says that in order for it to be continuous, the limit at that point from both sides must equal what the range value is here. So this is the two-sided limit, and this is just the simple old range, or ordinate value at that same point. And those have to equal each other if something's continuous. And again, that's because you're converging, and the same thing you're converging to is also your output, and so those are just one and the same thing. If you just think of the intuitive or graphical structure of what this means. So now that we have that down pat, it violates this. Those are clearly not equal. The two-sided limit here coming at 2 from here and here is 3, and the point defined is 2. So 3 does not equal 2, and therefore it's not continuous. Now let's look at the next one, where we have it x equals 3. And we have another discontinuity here, a slightly different reason for why it is not continuous. And that reason is, just checking my recording here, that reason is because the condition 3, I believe, is this, or excuse me, the limit must exist. Let's look at our list of limit rules. Yes, condition 2. Okay, condition 2 fails. The limit doesn't even, sorry, I can't, some books have them listed in different ways. Every book's a little different on which rule they want to give what name. So yeah, condition 2 here is violated, which is that the limit as x approaches 3 from both sides, the two-sided limit of f of x, doesn't exist. And that's because the limit coming from this way is 1, the limit coming from this way is 3. If the limits differ at the same juncture point, then we know that it can't possibly be continuous, because that's what a limit is, what you converge upon. It doesn't necessarily mean it's defined there to be a limit. So even though this one has a limit of 1, doesn't mean it's defined at 1 ever. It's not. All of these points are less, or above 1 rather, or different than 1. So it never actually hits 1, just has a limit of 1. Something interesting to note there. And so check and check, and we've now gone over number 5. So it'll be a really good task for you guys to go over number 6. All right. I'm going to pause the video there, and what I'll do I'm not going to pause it just yet. I'm just talking out loud, guys. I'm going to put a big number 11 here, move this out of the way, and if you've watched this long, if you're looking for a specific problem, I will keep those up so that you can kind of find them as like a old school way of doing a table of contents that you can scroll through, since sorry, we all got things. I can't get too fancy here. The key is making sure that we go over the problems and that you know what to do. But this will help. This way you can search for a problem the good old-fashioned way. Okay? And we're back. And let's do number 11. And if you read number 11, you will see that it said to determine the intervals of continuity. So I'm going to write that phrase down. Number 11 is right up here, folks. So intervals of continuity. And they want that interval of continuity for number 5 here. So where is the function continuous? And it's going to be continuous from, let's do this now. It's going to be continuous from 0 non-inclusive to 1 non-inclusive. So the function, this is the overall topic, this is the answer. The function f is continuous on 0 to 1, non-inclusive, that's why they're parentheses and not brackets. It is also continuous on 1 to 2. It's true, note that f of 2 does exist, but you don't have any concept of continuity at an individual point, because a point is an indivisible unit, and that means that there's nothing to the left of it and nothing to the right of it. So you can't possibly have continuity at a point. So the fact that there's a point defined at f of 2 is irrelevant to the fact that it's not continuous before and after 2, which is obvious because as you travel along it. But students do get hung up just wondering if this point has any impact and trying to explain why it wouldn't. And then the function is defined from 2 to 3 inclusive. And then lastly, our function is I don't know, I said defined, I think I meant continuous. From 3 non-inclusive to 5. So the next interval is 3 to 5 non-inclusive. So those are our intervals of continuity, and I hope that that helps. Okay, next up, we're going to do, let me get my list out, number 17. And then I'll probably stop the video and make sure everything recorded, okay? And we didn't get too big of a file for the laptop. All right, so number 17, we should now have written out. And again, hopefully you did that thing where you pause the video and you tried to do 17 on your own, maybe read out the examples, did the skim reading we talked about. But let's go ahead and do that now. So one of the things I noticed on problems like 17 when we did them together and when we saw them on your tests and different homeworks is you guys had a little trouble factoring these expressions. Remember, you want to go a times c, which is 2 times 1. The factors of 2 are 1 and 2. We want the ones that add up to be 3. That's these two. We want the sign pattern to match. That's going to be positive all the way around. So we start with x plus 1 and x plus 2. Now you might have been taught a different way. The way I'll teach you, so it's foolproof, after you check the sign pattern here, so plus and minus sign pattern, and then sum to b. So sum to b, plus and minus sign pattern for the value of c. And as long as these two things match, then what you do here is you divide a and simplify. So we're going to divide by a, which is 2. Okay, so this one simplifies to x plus 1. And this one, it's true, this is in what I call root form. So this is the root. It's the same as 2x, so the root is x plus, the root form is x plus 1/2. The factored form, okay, is 2x plus 1. And it's true that when both of these are set equal to 0, they both equal negative 1/2. So that's the similarity here, but it's for different reasons, and you may have in pre-calculus stopped when you factored here, but you should not. You need to, you can when you're just doing curve sketching and stuff, but you should not here. You need to simplify it to this form here. So divide a and simplify is that one there. What may also happen, and what the reason I thought this was a great problem to do together is because it happens here, is you may also need to multiply the factor back by a if it doesn't simplify. So when they don't simplify, or whatever part doesn't simplify out, multiply that by a and put it in factored form. The reasons for that are simple. If you expand it this way, then you're not accounting for the, when you did the sum of b to control for what you picked as your numbers here, if you don't multiply by a and you factor this back out, it won't come out to this, because it'll come out to a portion of it off by a factor of 2, because you found the factors of a times c, not the factors of just c like you're used to doing. So anyways, this is kind of a lengthy Algebra 1 recap on how to factor. This method, although this one's simple and most of you can do it in your head, it's a great problem to just step you through this way I do factoring, because a lot of students haven't seen that and they still have a great deal of trouble factoring, or they've just always guessed and checked and maybe they're tired of guessing and checking. All right, now we're going to deal with this one here, and we get the following. So we wanted to factor this just to be safe, just to see if any of these canceled with anything down here, and nothing does. And so I'm feeling pretty safe about making our conclusions about that. So again, the book kind of rushed on this problem, but you want to factor it here, make sure that there's no holes, okay? I don't see any evidence of holes. I only see that there's a vertical asymptote at x equals 0 and at x equals -5. So pause the video now and make your conclusion, and I'll write up a new fresh page. But this was just a bunch of scratch work to get from here to get to here, and then we're going to evaluate it at a equals -5. But again, we wanted to see if anything fell out, get our head around this function. To do that, we have to factor, so I took you guys down an Algebra 1 factoring review, which is something I do with my calculus students every year. You can write these steps down. They work every time, okay? So you do a times c factors, which I call the a times c factors. You have to sum them up to equal to b. You make sure to get the sums. That's not always just 2 with so few factors. It could be a bigger number and a lot of factors, right? Find the one that add or that multiply to have the correct sign pattern for the c value up here. So whatever 2 factors you pick, sometimes you can get 2 that sum up to the b. They need to multiply to have the same sign here. And then you just divide by a and simplify, and or multiply by a for whatever doesn't simplify. Sometimes they can simplify first, and then you multiply by whatever by whatever this reduced to, okay, which is not necessarily going to be a. So if that makes sense. So a, or the new a, is sometimes what I would tell students, because that would notice that pattern. At any rate, if you do this every time, it will always work. All of that was just to get this function, make sure that we don't have any holes, so that to make sure that both of these are in fact vertical asymptotes. And they are. So now that we know that they are, okay, we're going to write this again nicely, and we're going to make our conclusion like I was just telling you. I'm just coaching you through this. Let's pause our video. I'm going to pause mine as well. And I'm going to write up my nice answer for assessing the continuity at a equals -5, and you guys do the same. And since they were merely asking whether it is continuous at the a equals -5, we can merely say that x may not equal -5. And that therefore, I'm writing this out, sorry, let me pull up the cheese for you, and that therefore the function does not exist there. And can't be or not be continuous. You cannot even evaluate whether there is continuity there because it's not even a point on the domain of the function. So again, I fit in a free Algebra 1 review for you here for the numerator. And of course, none of that was strictly required, but it's always good to check your rational equations out to see what you have are holes, what you have are vertical asymptotes. Obviously at x equals -5, sorry guys, put in -5, okay, x plus 5, what makes the denominator 0? So that we're dividing by 0, right? And if we put in -5 here, which is exactly the point in question, we see that we get 0, and we can't divide by 0, so we know we have a vertical asymptote, and therefore x cannot equal -5. Okay, and so therefore you can't even assess continuity. So sorry if I went a little too quickly there at the start, and I hope that that helps. And sorry about that, guys. I made a slight mistake. I don't know why I said or not. Take that off. I was thinking of some other case, and my blood sugar's getting low. I had a little bread here. I feel a little bit better. So no, it can't be continuous. If it doesn't exist there, it's end of story. Again, you're thinking of the totality of the function f, which might have some stuff and a vertical asymptote, some more stuff and another asymptote, and then some more stuff, more stuff. Who knows what it looks like, right? We're not talking about this in particular. And when you're talking about that totality, you're talking about the continuity on the interval the function's defined, which spans from points over here, right, to points over here. And so on that totality of that interval, there's points where it's not continuous. So yes, what I was saying is true, that you can't possibly assess something somewhere where it doesn't exist. But on the totality of the picture or the plot of f, those are places at which you are not continuous, and that you are not continuous. So hope that helps. All right, and we're going to stop this video there and meet you in another video, and hope that helped.